Hi there. This video is going to be about electrochemistry. I want to point out a few things on the OneNote notebook here. We've got the electrochemistry lecture is going to go with this tab right here. If you look at the tab below it, which is labeled Reduction Potentials, this is a printout from the OpenStax Atom First Chemistry Second Edition of some tables in the back that we'll use that are the standard electrode potentials. So that's available for you in the OneNote notebook. So electrochemistry, I always think it's a shame that electrochem is pretty much the last concept that we introduce as a new concept in general chemistry, because it's got a lot of importance and applicability. And I usually talk about the several things that electrochemistry is. So one of the first things is that electrochemistry is just another way. I'll put ... because there's going to be more than one. Just another way to look at or measure thermodynamic favorability or non-favorability. Spontaneity, non-spontaneity, to use the old terms. So these are tables from a biochem book. The biochem textbook, in fact, that we use in our biochem book. And there's one more down here. And this first table is glycolysis. Second table is about the Krebs cycle, or the tricarboxylic acid cycle. And then the third one is about, well, it's a general table, but it's from the section on the electron transport chain. Or what's called oxidative phosphorylation. And what I wanted you to see here is that if you look at these energy values here, these are delta G. This one is in kilojoules per mole, and this one is in kilocalories per mole. For the old timers, the value in parentheses, let's see, actually I take that back. The value in parentheses is the kilocalorie per mole. The value that's not in parentheses is kilojoules per mole. And then the two columns refer to the different conditions, because living things generally, or at least humans, are at 37 Celsius, so that's a different sort of thing. And so for glycolysis, which is the first stage sort of respiration and digestion of a carbohydrate, we're thinking in delta G terms and kilojoules per mole. If you look over here at Krebs cycle, again, you've got delta G in kilojoules per mole, kilocalories per mole. When you get down to the electron transport chain, without fail, this is discussed in terms of MV or V. V is, of course, a volt. MV is millivolts, 1,000th of a volt. And this is in the language of electrochemistry. So in basically the same section in this biochemistry book, when they hit electron transport chain, because of the nature of the reactions that are there and stuff, which we don't need to go into any detail about, they shift from thinking about it in terms of thermodynamics to thinking about it in terms of electrochemistry. So this is one reason to get a good grip on electrochemistry. Now, the other thing that electrochemistry is it's an experimental technique. And in fact, it's a series of experimental techniques, I should say. I'll put that in period to probe the, delta G or E, basically thermo, unfavorability. So if you want to study the energetics of a reaction, electrochemistry is a useful technique. This is a diagram of a cell, and we can construct a cell, so that we have a voltmeter up here in the middle and measure the potentials of different cells. And in fact, that's how we get the data in tables that are like the one above there or the one on the other tab. So in a way, it's kind of analogous to calorimetry, which is the experimental technique for thermodynamics. And then the other thing about electrochem is a very important, is the basis of very important and pervasive technologies. On the left here, I have a picture of a hybrid car. This is a Prius. It has a gas engine and electrical motor, and a very large, complicated set of batteries. And what the car will do is actually charge those batteries, and whenever possible, use them to power the car, either in combination with the gas engine or by itself. It's about 50 miles per gallon. Is what those things run at. And we have two of these. We have one that looks kind of like this one, except it's not new. And that car paid for itself. I know gas prices are cheap right now, but when gas was pushing $3 a gallon or more, that car, the money that we saved compared to the car we had before, that car totally paid for itself. This on the right here, this is a diagram of a hearing aid battery. And so it's the same sort of thing. You can see anode and cathode there showing up as in the cell diagram up here. If you know anyone who has hearing aids, they're quite tiny, but they have to have a power source. If you, of course, you're quite familiar with your cell phones and the power sources of such things. So electrochemistry is really a quite important technology and kind of an exciting area in which to work, and something that can have a lot of applications to sustainability. If we're going to use different sources of power and store some of that energy, for example, solar energy that is collected during the daytime and made available in the night, we're going to need good battery technology, and that's all about electrochemistry. So I've taken up here, these are from the formula sheet. These are the collection of equations that are there, and we'll talk about those more if we use those. But you can see here, this is an equation that converts electrochemistry potentials and delta G's to each other. Okay, so the first thing that we need to think about is that electrochemistry involves redox reactions or oxidation reduction. We call redox reactions. And if you look in Chapter 7, Section 2, there is a big review there about redox reactions. We'll go through a little bit of that stuff, but you may want to look at that further, and that's why that's listed in the syllabus as a section that you need to review. To think about oxidation and redox reactions, we first have to remind ourselves about the concept of oxidation state. oxidation state is kind of like charge in that the oxidation state, kind of rule 2 is the oxidation state of a monoatomic ion is equal to the charge on that ion. So if I have Cl minus 1, that's oxidation state is -1. If I have Fe plus 3, that oxidation state is, you guessed it, plus 3. Now if I have Hg2 2+, that's a polyatomic ion. Can you guess what the oxidation state? The oxidation state here for each of the mercuries is +1. I've got +2 divided by 2 atoms to get that +1 for that. So and I guess that would be technically a homonuclear polyatomic ion would be the mercury 2 one, would be the case there. First rule of oxidation state is that if you have an elemental substance, meaning it's not charged, it's the element by itself, that oxidation state is 0. So if I have iron metal, its oxidation state, put the oxidation states up here, its oxidation state 0. If I have chlorine gas, its oxidation state is 0. If I have O2, its oxidation state is 0. If I have ozone, O3, its oxidation state is 0. If I have mercury, mercury liquid, for example, its oxidation state is going to be 0 in all those cases. There are some common oxidation states in compounds and polyatomic ions. And you're going to know most of these. Hydrogen is usually +1. If it's with something that is less electronegative than hydrogen, it could be -1. So that can happen sometime, but that's generally not common. Oxygen is usually -2 in a compound. There is one commonly discussed weird oxidation state of oxygen. If I have hydrogen peroxide, then you have the O2 2- ion, which is effectively O -1 in the peroxide. And halogens, if I have X, usually I refer to them, but fluorine, chlorine, bromine, iodine, they tend to be -1 unless with oxygen, in which case they're going to have positive charges, and that positive charge of course will vary, and if it's in an interhalogen compound, it's going to tend to be either +1 or -1. So if I have, for example, we'll look at an example later on. We start calculating those, and the thing we're going to use to calculate those is this equation, that the sum over all the atoms of the oxidation states is going to be equal to the charge, and I'll say on the species, and again, species can either mean molecule or it can mean ion. It's a term that I use interchangeably for molecules or ions. So let's take a look at that. So if I have H2O, for example, H being +1, O being -2 is what we'd normally get. If I do this sum, I'm going to have 2 hydrogens plus 1 oxygen. I'll put the elements there. and that should be equal to the charge overall, which is 0, right? The overall charge on this is 0. So if I have 2 times plus 1 for hydrogen plus 1 times minus 2 for oxygen, is that equal to 0? Absolutely. This is 2 minus 2 is equal to 0, so it checks out. If we look at hydrogen peroxide that we mentioned before, H2O2, now if I have 2 times plus 1 for the hydrogen, plus 2 times, I'm going to call it X for the oxygen, if that's got to be equal to 0, then we say, well, that's 2 plus 2X equals 0, so 2X is minus 2, so X is minus 1. This is the oxidation state of oxygen. And again, the hard part of this is that you've got to make this little equation, this that comes out of this summation, you've got to make it yourself. The easy part is that once you've got it, it's usually pretty easy algebra. So I always suggest that my students consider, if this were the final exam question in your math class, 2 plus 2x equals 0, you'd be thrilled to have that as your final exam. So the math's not that hard once you can create the equation, which is the hard part. Let's look at some other examples. Let's look at the interhalogen type compounds. So I set up here that when you have another halogen, that those can be either plus 1 or minus 1. So let's say I have the compound ICl. Okay, now both of these, tend to be -1, but they obviously both can't be -1, because if I have, -1 plus -1, that's not equal to 0. Okay, so that can't possibly be it. What would work nicely is for one of them to be plus 1 and one to be minus 1. Okay, that would work. Which one is plus 1, which one's minus 1? Well, if we look at our electronegativity trend, fluorine is greater than chlorine, is greater than bromine, is greater than iodine, and going down that row. So chlorine is greater than iodine, so chlorine wants the electrons more, so we would say that the chlorine here is minus 1 and the iodine is plus 1. Let's take a look at another species. So what about carbon monoxide? Okay, carbon monoxide. Well, so the oxygen, we can't really say that we know what the carbon is, but generally oxygen in a compound is going to be minus 2. So if carbon is X, my equation is going to be X plus -2 is equal to what? Well, the overall charge is 0. So that tells me that the carbon is plus 2 in this compound. Well, let's compare that to CO2. In CO2, our equation is X plus 2 times -2, and that 2 there is what? The 2 there, right? It's equal to 0 still. So X minus 4 equals 0, so X is equal to plus 4. So in this case, the carbon is in a higher oxidation state as it's in CO2 compared to carbon monoxide, where it's in the plus 2 oxidation state. And of course, these two compounds have very different properties, so that's explainable in part by their oxidation state of the carbon. Let's look at a polyatomic ion now. So if I have, let's do another halogen one. Let's look at the chlorate ion, for example. All right, so in this case, I'm going to have, I'm going to say that the chlorine is my X, because when halogens are in a compound with oxygen, they're not going to be -1. The oxygen's -2 is going to take priority over that. So my equation is going to be X for the chlorine. I've only got one of those. And then I'm going to have -2 for the oxygen, and I've got 3 of those, right? And then my overall charge is going to be -1, which comes from that overall charge here. So a little harder equation. X minus 6 is equal to -1. Still not too hard. Add 6 to both sides, and we wind up with X is equal to plus 5. So ClO3 minus is the X is plus 5. Let's just look quickly at the chloric acid, which is the acid version of this. Does making the acid change at all? Well, again, what can we know? Well, we know hydrogen is going to be +1, oxygen's going to be -2, but we're still not sure what that chlorine is. We're going to check that out. So now I'm going to have +1 for the hydrogen, +X for the chlorine, and +3 times -2 rather, for the oxygen, and that's all going to be now equal to 0 since the charge is 0. So we wind up with X, 1 plus X minus 6, that's 3 times, not 3X, is equal to 0. So X minus 5 is equal to 0. So X is +5, same oxidation state. Adding that hydrogen ion to it doesn't change the oxidation state of the chlorine and the chlorate. So you got to be able to do this. You got to be able to figure out the oxidation state of anything, and it's kind of useful if you can sort of get a sense of what the common oxidation states are for different elements, and recognize that if carbon, for example, is in the form of CO2, you can't oxidize that any further. That's as far as carbon goes in terms of oxidation. The only kind of reaction that it's going to be involved in terms of a redox reaction is one where the CO2 is getting reduced, and that would mean it would be oxidizing something else. So it's kind of a guide to predicting reactions. So let's move on to reactions then. So let's talk about oxidation and reduction. There are different ways of defining these, and I encourage you to consider all these different ways. You usually will find that one of them works better for you than not. So first of all, oxidation is described as the loss of electrons, and reduction is described as the gain of electrons. And folks say oil rig, oxidation is loss, reduction is gain. They also say Leo goes grr, loss of electrons is oxidation, gain of electrons is reduction. So there's a couple ways to remember that. The other way to think about it, oxidation is an increase in the oxidation state. Reduction is a reduction in the oxidation state. So that's the way I tended to think of it for many years, and that works pretty well too. Oftentimes, kind of generically, if you look at reactions, oxidation looks like a gain of oxygen atoms in the compound, and reduction might look like a loss of oxygen atoms in a compound. Or you might say that oxidation sometimes looks like a loss of hydrogen atoms in the compound, or reduction looks like a gain of hydrogen atoms in that compound. So you can see that sometimes as just sort of a general guide. That's the way a lot of biologists think about oxidation and biochemistry processes. You have to be careful with it, because just as we saw up there with the chloric acid example, adding that H plus to chlorate didn't change things. But if we just added a plain H atom, then it would have, if it were somehow HClO3 minus, that would have a different oxidation state. So I'll just show you that one real quick. If I had HClO3 minus, okay, which isn't something that normally exists, our equation would be +1 for the hydrogen, plus X for the chlorine, plus 3 times negative 2 for the oxygen is equal to minus 1. So x minus 5 is minus 1 now, so x is plus 4. So you see that adding a hydrogen to chlorate without it, with its electron, okay, where the negative charge stays there, gives you a reduction in the oxidation state. It goes from plus 5 to plus 4. Without that, the oxidation state didn't change if we just added the hydrogen atom as H+. Okay, so that's the difference between those. There are different ways to balance redox equations. Again, if you go look in Chapter 7.2 or Section 7.2, they talk about the half reaction method, which is a longer and probably overall more accurate sort of method, which you may have used before, may be familiar with, and may want to go back and rely on that. I'm going to use what's called a Latimer diagram. And, Latimer diagram is a term that gets used differently by different people, but what we're going to do is we're going to take our reaction and identify those half reactions in that reaction accordingly. So let's take a reaction that we use in the lab in Chem 111 and Chem 1. We take hydrogen peroxide, which is an aqueous solution, and we react it with permanganate ions, or potassium permanganate, and we do this in the presence of some acids, alright, H+, and what we get is O2 plus H2O plus a manganese plus 2 ion, and we don't have much in the way of details of everything else that's going on with that. Now, when we're analyzing a reaction in terms of redox, we need to go through and identify the charges on each atom. So hydrogen here is going to be plus 1. That's the oxidation state, rather, on that. Hydrogen peroxide, you remember, is that weird version of oxygen where O2 is negative 1. The hydrogen plus 1 is plus 1. O2 is going to be 0. H2O is going to be plus 1 minus 2. Mn plus 2 is going to be plus 2. Permanganate, if I do that equation over here, take it out over here. Well, that line's going to get confusing in a minute, so let's just make a space over here and say MnO4 minus, that's going to be X plus 4 times negative 2 is negative 1. X minus 8 equals negative 1 plus 8, X equals plus 7. So this manganese is plus 7. The oxygen's minus 2. Okay, so we look for the things that are getting oxidized and reduced here, and since this is an aqueous solution, we're not going to think about this water as necessarily being where this oxygen from peroxide goes. We're going to think about that as going from minus 1 to 0. Now, if I go from minus 1 to 0, is that an oxidation or a reduction? Well, let's think about that. I'm going from negative 1 to 0. My oxidation state is increasing. That's an oxidation half reaction. Now, how many electrons are involved in this? Well, there's 1 electron per oxygen, and we're losing or gaining it. We're losing electrons, so minus 1 electron per oxygen atom. We have 2 oxygen atoms, though, right? So this is going to be a negative 2 electron process. Now, that's our oxidation. Who's getting reduced? Pretty obvious that manganese at plus 7 is going to manganese at plus 2. That's a reduction, and that reduction is how many electrons. Find the number line is a useful thing to think about here. So if I say plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1, this is 0, negative 1, negative 2, right? All right, so we start at plus 7, we go to plus 2, that means 1, 2, 3, 4, 5 electrons, and if the charge is going down, electrons are negative, that's going to be plus 5 electrons per manganese. We have 1 manganese, so this is again going to be a 5 electron process. We now know that we have an oxidation half reaction that is a 2 electron process and a oxidation process that is a 5 electron process. What we need to do is apply coefficients to make the number of electrons gained and lost equal. So number of electrons gained, and that's got to be equal to the number of electrons lost. Okay, so that's required. Okay, so to make that happen, what we're going to do is multiply negative 2 by 5. That'll mean we'll be losing 10 electrons. We'll multiply the 5 electrons by 2. That'll mean we're gaining 10 electrons. And we take that number, the 5 and the 2, and put them in as coefficients in these processes. And again, you got to pay attention to the subscripts on everything to make sure the atoms are balanced as well. Now, we haven't balanced hydrogen ions and water in this. And if you go through the half reaction method in chapter 7.2, you need to do that sort of thing. But for most practical purposes, and if you're in the lab running this titration like you should have been, you don't need to know anything more than what we know right now, that the ratio of hydrogen peroxide to per manganate ion is 5 to 2, and you can work out what the percentage of hydrogen peroxide was in that lab using that information. The thing that we principally need to know here is what we call N, which is the number of electrons gained and lost here. So not moles of gas. Little n now stands for number of electrons gained and lost. So in this reaction, that's 10 electrons. 10 electrons, right? We've negative 2 times 5, positive 5 times 2. That's where we get that value of N as 10 electrons. Where that's important is the equation that I wrote up there before, that delta G is equal to negative NF E naught. That N is that number right there. So that would be 10. If we figure out the potential for this, we would be on our way, 2/3 of our way, towards getting the delta G for this. Okay, let's look at that then. How do we get E naught? For the cell, we call this. How do we get that? Well, what we do is generally we're going to take the E naught, get the E naught of the cell by taking the E naught of the oxidation half reaction plus E naught of the reduction half reaction, and we're going to pull those values from the tables. So our oxidation half reaction in this case was it was H2O2 going to O2 and giving up 2 electrons, and the 2 hydrogens probably look like they go to 2+. So that's oxidation half reaction. The reduction half reaction for this one was MnO4 minus, picking up 5 electrons and going to Mn plus 2, and we're not going to worry about the hydrogens. That's the core, the oxygens, that's the core of that. Those oxygens wind up in water molecules, presumably. But we're going to take a look at that. So let's go look at our table down here. So again, this is the table of reduction potentials that are in the book. And let's move through this and see what we can find. So here is a hydrogen peroxide reduction, okay, right here. And that's one thing to notice. If you look at this table, everything's written as a reduction. So H3O plus is just H plus, and then we've got the water molecules there. That doesn't look like the one we're producing oxygen, though, does it? Where we get O2 out of that. Okay, let's keep that in mind. Now we're looking for the permanganate value. Let's see. I'm looking for NMO4 minus going to Mn2. That's that one right there. That one right there. Still a little troubled by the fact that we don't have the hydrogen peroxide giving us oxygen gas in this reaction, even though there is a 2-electron transition. That's not describing what's going on there. So see if I look at my oxygen here. Here is hydrogen peroxide as a product in an oxygen reaction. So I think this is more the one we want, where we're getting O2 plus H2O2. And this hydrogen peroxide is the product of a reduction. So, sorry, product reduction. We turn it around. That's the oxidation, right? So what we're going to do is take that reaction, O2 plus 2H plus 2E. So it looks like this. So if we look at the table, we got O2 plus 2H plus 2E minus goes to H2O2, and that E naught, which is a reduction potential because it's written as a reduction, was I think 0.695, and that's false. Let's check that. Yeah, right. And then for manganese, okay, that's 1.507. So and there was I think 5 H pluses. Is that right? No, 8 H pluses and 4 H2Os. So 8 H pluses and 4 H2Os. Again, we didn't worry so much about the hydrogen atoms on the and the water molecules here, but that's pretty much our reaction. Now, the oxidation half reaction is not written the right way for us. This is a reduction. So if we flip this from the table, if we flip that, what we get is H2O2 goes to O2 plus 2H plus 2 electrons. That E naught is now an oxidation E naught. It's going to be negative the E naught reduction that we just looked at, so negative 0.695. And again, both of those are volts. So to do this reaction, okay, if we put them together, we've got 5 times the H2O2 goes to O2 plus 2H plus 2 electrons, and the potential for that half reaction is going to be negative 0.695 volts. And then we've got on the reduction side 2 times MnO4 minus plus 5 electrons goes to plus 8H plus goes to Mn plus 2 plus 4 H2O. And that's 1.507 for that potential. So if we get our overall reaction, 5H2O2 plus 2MnO4 minus plus 10 electrons plus 16H plus goes to 5O2 plus 10H plus 10 electrons plus 2Mn plus 2 plus 8 H2Os. If we cancel out some things, the electrons can cancel out. 10 H pluses cancels out 10 of those H pluses. We wind up with 5 H2O2 plus 2 MnO4 minus plus 6 H plus goes to 5 O2 plus 2 Mn plus 2 plus 8 waters. And if you go through and look at your atoms, I think we might be balanced there. We've got 16 hydrogens, 5 times 2 plus 6 there, and we've got 16 hydrogens over here. We've got 2 manganese. We've got 10, 8, 18 oxygens, 10, 8, 18 oxygens. So that's balanced atom-wise and molecule, atom-wise and redox-wise, electron-wise. The potential for this is going to be, again, that E naught is equal to E naught oxidation plus E naught reduction, which I labeled up there before. So that's going to be negative 0.695 plus 1.507. And that's in volts, of course. That's going to be a little less than 1. So I'll just do 1.507 minus 0.695. That's 0.812, and the units are volts, and that's positive. So there's a couple things to note. Okay, note, while for delta G, less than 0 is thermodynamically favorable. For E naught, or E, the cell potential, greater than 0 is thermofavorable. Okay, so that's something to note, that the signs are opposite. If we were trying to calculate delta G based on that, that's going to be negative NF E naught. That negative sign is what's going to take care of that. We said above that it's we got 10 electrons that being transferred. The Faraday constant is on the formula sheet. If we go back to the general section, or I guess it's in the review. Well, I feel like I should have the formula sheet here. Let's pull that out for you then. Okay, well, I'll just add it at the end here. Put the formula sheet here for us, which we generally have. So bear with me a minute while that comes in here, just so we know we have it. Alright, so the equation sheet is here, and the Faraday constant is right up here, and I just managed to write through it. The Faraday constant is here, and it has the same value with two sets of units, so 96,485 coulombs per mole or joules per volt mole. So if we go back and put that in, 96,485, 96,485, the joules per volt mole, I think matters, is the best unit for this, because our potential is 0.812 volts, okay, that we just calculated above. So that's going to come out to be 10 10 times 96,485, that's going to be almost a million, times 0.812, so around 800,000 maybe, and that comes and put the negative charge in. That's negative 783,458 joules per mole. Or if we convert that to kilojoules, 1 kJ over 1,000 joules, that's going to be negative 783.5 kilojoules per mole. And that's our delta G value for that. And notice the big difference in the scale of those values. This potential value that's not even a single volt translates to a delta G that's quite substantial. It's almost 1,000 kilojoules per mole, which is very high for chemical reactions. If you've been doing the calculations with chemical reactions, you see how that goes. So anyway, so that's going to sum up the first first video on electrochemistry. There's a lot of stuff to review here. You've got to be able to do oxidation states. You're able to figure out the more complicated oxidation states, identify oxidation and reduction processes in a reaction, and then balance that reaction and calculate the standard cell potential, E0 cell, from the half reaction values that are tabulated, and then convert that to delta G for a reaction. So you've got a number of things that you can do at this point, and we'll tackle more stuff in the next video.